The second model is Markov Random Fields. So an MRF is an undirected graph in this case. Remember, Bayesian networks were directed. In this case, they're undirected. And again, each node represents a discrete random variable, and edges correspond to some notion of direct probabilistic interaction. So these models, if you look at the history of where they came from, they were born out of research in physics. I think it was ferromagnetism, that they were studying the interaction between particles of a certain kind, and they wanted to model how these things worked. So that's why they are undirected. So both particles influence each other. And this interaction is parameterized with potential functions, and there will be one potential function per maximal clique. This is pretty opaque if you read it like this. So there's an example on the next slide. And these potentials, they are essentially non-negative real-valued functions. They're just functions, nothing to be scared of. They are called potentials again because they come from physics, and they are measuring energy. And they are values that are that range over the values of each clique in the graph. So the value for each variable in each in the clique is called the state of the clique. And this is where it's simpler in this case. So than the Bayesian networks, a node is conditionally independent of the rest of the nodes in the graph, sort of like what I mentioned for Bayesian. But in this case, it's only given the values of the immediate neighbors. So that's referred to as the node's Markov blanket. Again, it's the same concept, but as we see in this case, it's simpler. We'll come back to this in a bit. So, example. We have, again, Boolean variables for the day is sunny, it's hot outside, we go to the beach, and we go on a walk. And here in colors, we see the cliques. So in this case, they're pretty simple. They're only two variables per clique, but you can see that they're linked together. So there is some interesting stuff going on. So the potential functions have to encode somehow, and this is one of the more cryptic aspects of this model, somehow encode what you want the setting to be, to have with respect to probability values. So if you look at these values, it makes sense that, for instance, if it's sunny, it's more likely that we won't take a walk than we will. See, the weight of that is greater than the weight for this. Why, one might ask? Because it would be nice to go out when it's sunny, have a walk. But in this model, the user being modeled is probably more likely to go to the beach. So if it's sunny, they want to go to the beach. So let's look at the yellow clique. If it's sunny, it's more likely that I will go to the beach, 1.7, than if it's sunny, not going to the beach, 0.2. So, I won't go into these numbers in much detail because it's a little bit boring, but this is the kind of thing that they are encoding. And we'll see in a minute how we get probabilities from this, which is the main goal. The joint distribution, then, the same way that we did for Bayesian networks, is defined as follows. So we have the potential functions. So we have one a generalized product here. I ranges over all the cliques, and all we have to do is multiply the values that the potential function has for the state of the clique that is given by the world that you want to query. And then we have this z value here, which is a normalizing constant. This ensures that the sum of the probabilities will all be equal to 1. So I have a worked out example so you can see this based on the same thing. So let's calculate the probability that the day is sunny and hot and that we go to the beach and not on a walk. So this is the one value per node, and here in the arrows we can see where each clique gets its state. So why do we have it here? Because it's sunny and we don't go to a walk. Sunny, no walk. So we get a 2. This 2 gets plugged in here. Multiplies by 3 because we have a hot day and we do go to the beach. So we get a 3. And the same, we have, we go to the beach and it's 1.7. So 2 times 3 times 1.7 is 10.2. And Z, there's another example in a bit where we'll see exactly how Z is calculated, but it's simply do this math, the 2 times 3 times 1.7 for each possible set of settings of these variables. Can somebody tell me how many there are? I have 4 variables. So I guess you're muted, so I can't hear you if somebody's answering. 16, thank you. All right, so we could just do that 16 times, we'll get 16 different values, and we sum them up, and that will be Z. That's how we get this value. So the probability of our query is about 12.3%. All right, so one of the issues here is similar. I didn't mention them for Bayesian networks, but Bayesian networks have, one of the problems is that you probably saw it with the alarm node that has 2 parents, and the CPT had 4 entries. That's because it's 2 squared is 4, and if it had 3, it would be 8, and if it had 4, it would be 16. So these tables grow exponentially with the complexity of the way the edges intertwine in the graph. So this same kind of thing happens in MRFs. Expressing the value of each state of each clique is exponential in the size of the cliques. So here we have, each clique has 2 variables with 2 values, and that's why they only have 4. But imagine again if it had 4 or 5 different nodes in there, then it would be much longer. So one way of getting a more compact representation is using functions called features. And in order to do this, we'll present them. It's a little bit simpler than math, but it's an equivalent formulation called a log linear formulation. So instead of having this product of potentials, we'll have an exponentiated sum, weighted sum of the feature values here. So it's completely equivalent. You can do the math yourselves if you want. The I also varies over the cliques, and Z is again the normalization constant. It's the same thing, except that you do e to the power of a sum instead of doing just the products. So now these features, they're also real valued functions over states. They replace the potential functions, but it's a way of summarizing different values into one. We'll see a quick example now. So each feature will have associated a weight as well. And that's where this W came in. And so the most direct translation from the original form that we saw at the beginning would be there is a feature corresponding to each possible state, with the weight just being the logarithm of the potential function. So, for example, if we just wanted to say, I'm only interested in saying that if sunny is true and walk is false, I get a 1. So, the feature is on or it's off. Then that's one way of summarizing 4 different values. And then we would have to also assign weight to this. We'll come back to this immediately because the next model that we're going to cover is Markov Logic Networks. So an MLN, also commonly referred to as just Markov Logic, is a finite set of pairs, just Fi, Wi, where Fi is a first order logic formula of the kind that we saw in the last week's lecture. just a regular formula. And the WIs are just real numbers, so the weights. And together with a finite set of constants, so we have n different constants, this defines an MRF. It's only a template, so Markov logic is only a template that will generate a Markov random field given a specific set of constants. We'll see a quick example of this in just a second, another very, very classic example. So we'll see how this maps to what I just said for MRFs. The model will contain a binary node for each possible ground instance of an atom in the formulas. Ground, given the different constants that I have. The node's value will be 1 if the atom is true and 0 otherwise, very direct mapping. The model will contain a feature, the ones that I just mentioned, for each ground instance of a formula, so one of these guys, in the original model, and the value again of the feature will be 1 if it's true and 0 otherwise, and the weight will be directly the weight that I'm giving it here. So from this definition, if you paid attention, you can derive a few quick observations. So the ground atoms are the ones that are going to generate the nodes in the network. So there's going to be a one-to-one correspondence between ground atoms and nodes. And nodes, if you remember from before, they correspond to random variables. So now we have ground atoms connect to random variables. And there's an edge between nodes if and only if the ground atoms appear together in at least one ground instance of a ground formula in NEL. This is again because of the way it's built. And because of this, formulas generate cliques in the network, because if each time they appear together there's an edge, then you can work out the example that as we will do in a second, and you'll get a whole clique. Right, and that's how, remember, cliques are associated with features, and the features of the formulas themselves. So there's a very nice one-to-one correspondence between these structures. So let's consider a Markov logic network defined by just two simple pairs, and this is again a very very classic example of I think they typically refer to as friends and smokers. So we have that first order logic formula for all x. If x smokes, so smoking leads to cancer, essentially. If x is an individual who smokes, then x has cancer with a certain weight, 1.5, so smoking leads to cancer. And then there's another one that looks more involved, but it's pretty simple as well. It says, for any pair of individuals who are in the friendship relation, so friends x and y, either they both smoke or they both do not smoke. So the smoking status is equivalent. The smoking status of friends is equivalent. Either they both smoke or they both don't. This, of course, does not model reality in very closely, but as an example, we can see what would happen. So remember that I said that the MLN is comprised of just a set of pairs, weighted pairs, and constants. So given constants, now we can get our Markov random field and do some queries. If we do that, then we can say, for instance, we can ask, what is the probability that Anna and Bob are friends given their smoking habits? So maybe I look at these two people from far away, and I see that they're both smoking, and I have my model. I'll plug it in and say, I wonder if they're friends. So I can do that with this model. Or the probability that Bob has cancer given his friendship with Anna, with different, depending on what evidence I have, if Anna herself has cancer, and so on and so on. So this is what's going to happen if I ground out the formulas. So if I have, this even has some obvious or redundant nodes like friends, people being friends with themselves. But it's just a a direct grounding of the friends and smokes and cancer predicates with constants A and B, right? So we don't even assume that friends A and B is the same as friends BA. So as you can see, smoking leads to cancer. So if I have smoking and cancer, these two are joined here. Any two atoms, ground atoms, with the same individual here with the same constant will be linked by an edge. And the same thing here. If they are individuals that are friends and they're in the smoking relation, they'll also be joined with an edge and also smoke between themselves. And here's a clique. And so I promised you probabilities. Probabilities, of course, are the same as the ones from the Markov Random Fields, because that's all Markov logic is. Remember, it's a template where I have formulas. I want to express through the weights which formulas I think should hold with more probability. And the probability is yielded by the same formula of the underlying MRF. There is one detail, though, that since I'm dealing with features, there's one small thing that we have to this is just a consequence of the formula, but it's a simpler way of thinking about it. Instead of having here the value of the feature, I have the number of ground instances that are satisfied by X instead of just having the feature. Because if I just had the feature, I would still have to do this, and I would have one for each one of the ground instances that are satisfied. So we just have this abbreviated form, right? And Z is again the normalizing constant in the same way as it was before. I also promised you a full example of this before, so let's do it. This is another kind of toy example where I only plug in one constant so I can do all the math. And so here I have essentially P. I didn't include the for alls here, but it's P implies Q, P implies R. So P implies Q, P implies R, and S implies R. And the different weights here are, 1.2, 2, and 3. We only have one constant C, and the set of ground atoms is then just these four variables. If I had more constants, in this case, it wouldn't be that interesting of a graph because there are no, it's always the same formula. So it's always X. So I would have another copy of this for each constant. So now we have, as before, 2 to the power of 4, 16 possible assignments of values to the variables. And the probabilities are as follows. So this is an example that I worked out fully for a paper. I could never find good examples in any of the papers, so I did it myself. So I pass it on to you guys. So I have 16 possible worlds. I have the different, remember the ground atoms are random variables that can each take value false or true. And then here is a column where I have to check which formulas this world, call it the lambda 1, the all false world, which ones it satisfies. In this case, it's all of them. Why? Because if I have false in the antecedent of an implication, the formula is always true. Right? That's just a consequence of the way it's defined in logic. So in this case, they're all satisfied. Why do I drop 3 here? Because here we have S equals true, and S is the antecedent of this. So true implies R, which was false. It's false, so it's not satisfied, right? So I can do that for all of these possible worlds. Some of them won't satisfy anything. Some of them will satisfy all of them, some only one. And following this formula, n will always be 1 because I only have one ground instance of each formula. All I have to do is do e to the power of the sum of these weights. So the weights are here, 1.2, 2, and 3. 1.2, 2 plus 3 is 6.2. So e to the power of 6.2 divided by z. How did I get z? All I have to do is sum all of these like I did before. And that will be my z. And when I divide it by z, I get this. So if you do the math, these numbers, unless I made a mistake, should all sum up to 1. An interesting thing that happens here is in worlds 9 and 10. So 9 and 10 have no, they don't satisfy any of the formulas. But the way these models work, you don't get a 0 really, because the potential is 0, but it's still e to the 0. So the 0 is 1, right? So it's 1 over z. Z is a pretty big value in this case. I think it's in the thousands. Yeah, there it is. It's 3,891. Here I say it's almost 0, but one of the properties, one of the fundamental properties of why all of this works as a probability distribution is that no world can ever receive a value of 0. It's just one of the things that it's in the fundamental theorems that I'll mention in just a bit. And another thing that we'll see in just a second related to Markov chains is that if this were in fact a 0, then it would mean that it would be very difficult to approximate the probabilities via random walks or impossible in this case, where I had to do certain distributed random walks in order to do it, because I wouldn't be able to traverse the space of possible worlds. But more on this in just a second. Sorry if it was cryptic. So here's a little bit more about exactly how I calculated this. This is the z here is just the sum of this. And if we wanted to calculate the probability of a formula like P of C and Q of C, all we have to do is, as usual in these possible worlds approach, is to sum the probabilities of all the worlds that satisfy this formula. That in this case is worlds 13 through 16, the ones in red here. So it would be, this number here is about 27.1%. If anybody has any questions, feel free to stop me. So a few concluding remarks for MRFs and MLNs is this fundamental theorem, the Hammersley-Clifford theorem from the 70s. I'll only mention it intuitively because in order to do it formally, you need more tools, but the result relates, it only holds for strictly positive distributions, which means what I just said before, that no world has probability 0. And it relates conditional independence. So this property that I said that was so great, that you can just have the Markov blanket be the neighbors of the nodes, it relates that condition with, or that property with the possibility of doing the factorization of the joint distribution, the same way I did for Bayesian networks. Remember where I had the alarm and had the different factors of the joint distribution. That's a very important thing computationally, because otherwise you'll have, if it were just specified as a table, then you would have to pay exponential space to store it and exponential time to query it. So no good. For interested readers, there's a link here with some of this material on this theorem and some history and where it came from. And somebody thought they had it at some point and they published it before, but then this other guy came and fixed it, and that's why it's called the Hammersley-Clifford theorem. And So as I mentioned, the probabilistic independence is very simple to determine. It's just given by graph separation. So in particular, this means that the Markov blanket is simply comprised of the immediate neighbors, and therefore a variable is independent of the rest of the graph given its neighbors. We'll see an example of this in just a minute with the next model with Markov chains and what that means. Unfortunately, exact computation is sharp P hard. I don't want to get too much into this, but sharp P, I mentioned it also for Bayesian networks. Sharp P is the class, it's called like the counting class, where the typical canonical problem in that class is sharp sat, where instead of saying, given a formula, tell me if it's satisfiable or not, sharp sat wants to know how many satisfying assignments it has. So can somebody tell me why they think computation is sharp P in Markov Random Fields? Any guesses?
Hey guys, the sharp P problem is giving the number of solutions to a problem. It's considered very hard is you could potentially have an exponential number of like satisfying assignments to a formula, for example, the counting version of SAT.
Right, so the reason is because it's right here in blue. It's because I have to go through all the worlds just to calculate Z. So this normalization factor, which is at the heart of getting a probability, if I don't have that, I just have just numbers, then I could just encode sharp sat in one of these
We got a couple of questions.
Oh yeah.
So just from my understanding, because I usually don't pick things up on the first one, if we're trying to get the normalization factor, like sharp P just means that when going through all of these worlds, in a small discrete problem where there's only like 4 nodes, that's not a problem. But if I have, say, a whole network that has, 10,000 nodes, going through all the worlds of those 10,000 nodes in combinations was effectively a monstrous supercomputer to even begin starting to
Exactly. Yeah. So I guess your question is, how is this useful?
We have one other question.
Yeah, so I'm just confused how it's like what's the difference between sharp P and like just not like NP? Because I mean, wouldn't the runtime be 2 to the n? Right?
So an NP hard problem, so sharp P is just a harder class than NP hard.
Oh.
And with a sharp P hard problem, so with an NP complete problem, you're guaranteed to have a certificate that's in polynomial time. You don't have that with sharp P.
Okay.
Yeah. And you go back to what you were saying, Jerry.
Yeah. So basically, what the difference is that with if you look at SAT versus sharp SAT, it seems, at least intuitively, easier to say, well, I wonder if I can plug in values for this in such a way as to satisfy it. Maybe, I get lucky and I do it, or I find some special cases where I can do it quickly and I just have to do a thumbs up, thumbs down. But sharp SAT is much more demanding. It wants to know exactly how many there are in such a way that that you satisfy or you don't. And I mentioned briefly in the Bayesian networks section, I mentioned PP, which is the decision version of sharp P, which is just say, are you above a certain threshold? So are at least 35% of the possible assignments to this formula satisfying assignments, or are they not? That's the decision version of the counting problem, and they're closely related. They're both very, very hard. So the reason why is essentially that this normalization constant. And to the student who was asking the question, as like what do you do if you have a 10,000 node Markov random field? Well, the question is, you probably will never want to calculate the exact values of this, and that's why we'll see the Markov chains in just a second, and you'll see the magic of this graph separation. Well, you won't see the magic because it's in a small example with the 4 nodes, but hopefully you'll get the taste of where the magic comes from. And when I say magic, I just mean cool math, of course. And also, Bayesian networks can be converted into Markov random fields if you were so inclined, and through certain transformation algorithms. And that's sometimes useful for approximate query answering in certain cases. I mentioned that Bayesian networks are good when the graph is simple, so there's not very much, there are many intertwined edges. But if there are, then you can also, do this. Transform it into an MRF and go to town on. So the much promised Markov chains. So you probably heard about Markov chains in the past. Also, they're mentioned a lot in many different scenarios. They're essentially what they call stochastic processes. They're the form, you have different variables and different variables. Where there's a natural number of them, and they represent an evolution of a system through time. We'll see another very simple example in a bit. And they also satisfy the Markov property. This is another term that's quite overloaded. So the Markov property, we just saw Markov chain, Markov random fields, Markov logic. And in that case, there are other Markov properties where it depends. It's all the same class of properties where you say, oh, you only have to look at certain things. So the Markov blanket in that case. But in this case, it just means that it's much easier to remember. Ironically, it's called the memorylessness property. So you don't have to remember the whole trajectory that you took to get into a certain state. All you have to know is where you are right now. So that's encoded quite simply through this formula where I say the probability of xn plus 1 given xn and all the history, it's equal to just knowing where you are now. That will tell you what the probability is of where you're going. So the probability of the future only depends on the current state. And the chains can be represented as sequences of graphs labeled with the probability of going from one state at the moment n with another in the future. So the one that we just saw. Or it can also be represented with what's called the transition matrix of the form that is shown here from time n to time n plus 1. Right? So where you have each of these elements in the matrix is just encoding these conditional probabilities. We'll see an example, a very simple example soon. And given that the probabilities must sum to 1 of transitioning from state I to the rest of the states, we have that the sum of different rows has to be 1. So, example, suppose we classify jobs, jobs is in general, it could be either low, middle, or high wage. So the difference, how much money they get paid for doing the job. And suppose further that the most influential factor for the kind of job that a person will have next, so the next job that they'll get, is the job they have right now. So that's a pretty standard thing to think about, right? So if you are a person with a low-paying job, you're in state 1, medium-paying, state 2, high-paying, state 3. So if we see that the most common is to stay where you are. So the diagonal of the matrix is, for instance, if you're in a medium-paying job, the most probable thing is that you're going to continue being there. You might hop to a higher-paying job, or go down to a lower paying. If you have a low paid job, then there's a reasonable chance that you'll get a medium paying job next, but there's a very slim chance that you'll get a jump to a high paying job, right? So it's just a stochastic process. Just think about it in that way. These diagrams, I'll actually, like an automaton, help in that way. So you can see here the self loops are the ones that I just mentioned, and just transitioning from one to the other are the same probabilities that I encoded in this transition matrix, which can also be as a matrix in matrix form, as I just mentioned. So now we would like to know, for instance, a kind of query that you might ask of this model is, what's the probability of changing class, wage class within the next 2 jobs? So I want to know, in a couple of jobs, where will I be? What's the probability? So if a person is currently at a high paying job, state 3, what is the probability that they will be in state 2 in 2 jobs from now? So that'll be one step down. What I can do is, one way of calculating this very intuitively is just, on state 3, I have I know the probabilities of moving to 1 to 2 and to 3, so they're labeled in this way. Just got them from the transition matrix. And then again, because I want to know 2 jobs from now, again, the same values from 1 to 1, from 1 to 2, 1 to 3, and so on and so forth. And I'm interested in what's the probability of reaching state 2? So here with the arrows, I have ones where I end up in state 2. These are just multiplied, by the way, because they're independent, right? And I can just sum them and get this value, around a little bit less than 50% chance. Another way of doing that is just taking, this is where the very interesting math starts happening. I can just take the square of the matrix, the transition matrix multiplied by itself, and take element 3, 2, which means transitioning from 3 to 2. In this case, because it's squared, it's in two steps. And I get the same result that I just got doing the tree. So Markov chains, they're not all as pretty as this one. Markov chains are regular if some power of its transition function contains all positive elements. So it's not always the case. And if a Markov chain is regular, then this is a property that there exists a unique vector V, such that for any vector of probabilities V and large values of n, so if I do the iteration enough times, then I will get this vector V, and vector V is called the stationary distribution. And to find V, we can solve an equation of this form. I'll show you just a bit, using the fact that the entries must sum to 1. And the powers of the matrix multiplied with itself get iteratively closer to the matrix with rows that correspond to the stationary distribution. Let's see how that works. So I can solve this system of equations like I was just mentioning. They're sum to 1, and I get this vector. And this should be the stationary distribution. And if I do, I'll just hand wave this because I don't have a way of doing it, of course, to the limit, because I have finite time. But if I do p to the 4th power, I get this matrix. P to the 10 already looks kind of like it's going to stay. There are a couple of variants here, but p to the 16 already, at least for 2-digit precision, is already in the same, very close to what I just called the stationary distribution. So a cool visualization tool, if you want to play with it, you can have these. They're also for more than 2 variables, but you can play around with the sliders and it animates this, and it'll you can get some ideas of how these things work with an interactive tool. And a key application, why am I even talking about all this, is that Markov chains are the basis of many algorithms based on sampling from a probability distribution. Why would I want to do that? Because sometimes I want to see how the probability of a given query is, or something like that, like I was just mentioning in the examples before. And in particular, they're at the core of a family of methods called Markov Chain Monte Carlo. So MCMC, Monte Carlo, because there's a casino, a really famous one in Monaco called Monte Carlo. Here's a picture for your enjoyment. And I don't have time. I already see that I only have less than 15 minutes to finish, but I'll let you go through these an example of this method, which will let you see, as I was promising, the power of the conditional independence in Markov random fields, for instance. The method is quite simple. So we want to approximate a distribution. The method is based on the idea of simulating a Markov chain with this is where the tricky part is. You have to simulate a Markov chain such that the stationary distribution is exactly what you want to approximate. So that's a property that you have to prove somehow. So we start at a random state and generate the next state iteratively by taking samples of the value of one of the variables, conditioned on the current values of the variables in the Markov blanket. So, and the stationary distribution can be approximated by executing the second step a sufficient number of times, typically referred to as the mixing time, until you get an approximation of the probability that you're looking for. And the interesting thing about this is that because it's a Markov chain, each sample depends only on its predecessor. So all you have to do is you have to do it a lot of times, but it's a simple thing to do. So it's a really simple calculation. The probability of a query can also be calculated with the same kind of random walk structure. This is the one that I don't have time to go through all the details, but this is where you can see that you can sample, like you can start with a random assignment, like, okay, it's sunny, it's hot, it's we're going to the beach and not on a walk. And my query is, hey, what's the probability of going to the beach given a sunny and hot day? It's probably pretty high. I would say if the model is right, it's sunny, it's hot, let's go to the beach. So you start with one of your states just randomly assigned, and then you can sample, for instance, you can sample from walk given its Markov blanket. Walk is right here. What's the Markov blanket? It's just sunny. So you can do a very simple calculation based on this conditional independence, the way that I do here, the same kind of thing that I do here to calculate the exact value compared to what I got. And from there, you can say, okay, my next sample is, my next state is, walk is true, for instance, sunny, hot, beach, walk. So suppose I do that 10 times, very small number, but suppose I do it 10 times, and we visited beach equals true 9 of the times, and just 1 in which beach is false. So I was interested in beach equals true. So my approximation would be 0.9 against 0.1. And the exact value is 0.94. You can do the math with the potentials from the original slide 14.